Hello, Assalamu alaikum. So this is my second lecture in the online education continuum series. So basically, previously we discussed about corners, and we mostly discussed about Harris corners, the stability of uh, the corners or the patches which needs to be selected in order to uh, let image in order to match a particular patch between two images, and it is also used in different purposes like image stitching and image matching, and we'll discuss this in this lecture with a demo. The thing which I need to say here is previously my lecture videos had some issues with respect to the voice recording, so the voice was quite slow. I hope that I have resolved this issue now, and this video will be clear in terms of voice. So the students will have not and will not have any issue regarding the voice problem which was experienced before. Another thing which I need to discuss here is that there is a lot of problems going on in online sessions. I understand that because we are not used to of conducting online sessions. So it is first time for us for delivering the lectures in this sort of medium through this sort of medium. So I would request the students, so please also bear with us and kindly provide the suggestions rather than exploiting those problems in public, and it will be easier for us to tackle this situation while working together rather than uh, playing a blame game with respect to the online lectures and uh, the system which is in play right now due to this COVID-19 pandemic. So let's start this lecture and hope that everybody is fine and free from COVID-19 disease. So today we are going to talk about feature descriptors, and these feature descriptors are mainly used for image matching, and they can also be used for image stitching, panorama images and all that stuff. The main point is like we discussed in the previous lecture, that we need to select a patch which is a kind of stable and unique in terms that it should have a single peak, and if it is having a single peak, then it will be easier to detect the same page in another image, so that we can perform the operations which are necessary for that particular application. So let's start the lecture. So this feature descriptors, let's say we have these two images. One is the normal image, and the second is a kind of a rotated and scaled image, rotated, translated and scaled image. So there are three transformations going on. We can say that it is also representing an affine transformation with a little more scaling. So what we need to do here, first we need to find a set of distinctive key points, and I have already discussed that in my last lecture, that we need to find the points which are unique and which represent a single response rather than multiple responses. So in this case you may see that these are the corners in a sense that the gradients are in all directions, not just one direction. So there the gradients are in multiple directions. So these points can be considered as a distinctive key points to be extracted for image matching or for any other operation which we need to perform. The second step would be to define a region around each key point. So we need to define the region so that we can extract the descriptors from that particular region. And third is to extract and normalize the region content. So if we extract and normalize the region content, like let's say we should consider aligning them, so it will be easier for us to match and compare both these patches. And then we need to compute a local descriptor from the normalized image. One of the option is to extract the histograms. We will discuss about histogram of oriented gradients later in this week, but let's say that we need to compute any of the descriptors from these normalized regions. We can compute shift, that is scale invariant feature transform. We can compute corners, we can compute histogram of oriented gradients, we can compute local binary patterns, local phase quantization. So basically there are many descriptors available, and we can extract any of the uh, descriptor descriptor extraction method from these normalized regions. And then we need to match the local descriptors, and it can be done by matching the similarity, or it can be done by comparing it with any other method. So there are a lot of other methods which can be used for such comparisons. So we have already discussed about Harris corner detection in our last week, and we already discussed that why we focus on the corners, because there are some flat regions, there are edges which provide the responses in a single direction, and there are corners where we can get the response in multiple directions. So the gradient is in all directions or is in multiple directions, so it is easier to find that distinctive pattern in another image rather than looking for the edge, which will give us many false responses. And one way to compute this corners was the Harris corner method, and we already discussed that how we can compute it. So we can compute it by computing the determinant and trace, and using this formula for computing the responses. And these responses can be computed using eigenvalues and eigenvectors. We have already discussed it in our previous class, that how we can consider the eigenvectors and eigenvalues for detecting the corners. So basically, if we avoid computing the eigenvalues, and if we use the constant values from 0.4 to 0.06, the alpha value in this case, it will yield a faster approximation. Remember that we are talking about approximation, and in our uh, previous course, the numerical methods, we have already detailed we have already discussed in detail that what approximation means, what the numerical methods can do. So the numerical methods can yield the same approximated results with less time, or sometimes where there is no analytical solution available, we can provide that particular solution using the numerical methods. So basically this is an approximation method, so of course it will not yield the exact value, but it will provide a faster computation for detecting the corners. So this is one example of Harris corner detection, and as you can see that if we detect the corners, or if we apply Harris corner detection, we'll get these points which are the most stable pages, and you can see that these are the most distinctive patterns. So it will be easier to compare this image to this image, and it will be uh, stable to match these 2 points and extract the object which we want to match or which we want to discover. But there are some problems with Harris corner detection, and the problems are these. So you can see that these are the corners which does not have anything to do with the image which we are providing to match. So basically this is a kind of a false region which we want to eliminate. One thing more which I discussed in our previous lecture was that corners can be translation invariant. So if you translate or if you shift an image, so there will be no problem in matching the patch, and we have already saw this with respect to one demo in our last lecture. And it is also rotation invariant. So if you like rotate the object, it will still uh, detect the corners as it is. But the problem is with the scale invariant. So it's like if you scale a particular curve like this, so here we have the corners, so we can detect the corners, right? But if we scale it, we can only detect the edges, so there are no corners to it. And this will create a problem when we consider matching the image, because a certain type of corners would not be detected in another image if it is an scaled version of it. So the same patterns could not be detected, so they will not be a kind of a distinctive patterns in another image. So the corners are not prone to scale invariance. So if the image is scaled, then probably the corners would not work in that case. Now, why scale creates the problem? So if you can see here, if we detect the corners, the scale of the window you use can change the corners you detect. So in this case, you are detecting this corner, but if you scale it, see, there is a shift in the change, and you cannot detect the same corners as you are detecting in this image. So there will be a problem here. So see, there is a problem in the detection if you scale it, of course. So what we do is we consider regions rather than just considering a point. So we consider, for instance, the circles of different sizes, and we find regions of the corresponding sizes that will look the same in both the images. So even if you scale it, if we can detect the same region, or if we can detect the same shape of circle with a certain descriptor which is already defined, we can compute that particular descriptor from that region, and then we can match them accordingly. So in this case, if you scale it, if you define different regions with respect to the varying scales like these circles, then you will be able to see that which of the descriptors in this region can match the descriptors defined in this region. But what you have to do is you have to look around different scales. You have to change the scale, then you have to look it again, and then you have to change the scale, then you have to look it again. So it's a kind of a iterative process where you look for a particular scale which will be fit for the comparison. But the problem here is that how we choose that corresponding circles independently in an image. So the problem is that how many scales you would try, how many scales you would look for, because this is a certain line. It's easier to visualize the difference, it's easier to understand the concept. But if you consider a particular image, the image can be of 640 by 480 pixels, so you can imagine that how many pixels would be there, and how many regions would can we extract from that particular image. So it will be difficult for us to practically look for all the scales available within our possible range. So it's like we are looping again and again and again for that particular scale which we are looking for, and then we are defining, comparing it with the region constantly within the detected scale. So it will be very difficult for us to basically run that algorithm for near to infinite times based on the resolution which we have been provided. So it's very difficult for choosing the corresponding circles or choosing the scale itself. So the solution is we should design a function on the region which is scale invariant, like uh, we can do it for the corresponding regions if they are at different scales. For instance, we can look for the average intensity. So for corresponding regions, even of different sizes, it will be the same. And this is one of the examples. So for a point in one image, we can consider it as a function of region size. Let's say circle size. So let's represent this x-axis as region size and the y-axis as the function. And you will find it very similar to our numerical methods theory which we have studied in our last semester. So if how we define the function and how we consider this x-axis to be the shift or the change relative to the function which we have designed, so you can easily relate to it, and you already know different kinds of methods which can be applied to compare it iteratively. So coming back to this concept, for a point in one image we consider it as a function of region size, let's say circle radius. So even if we scale it to the size half of it, so still we can find a particular peak, or we can find a particular response which is similar in both the images. So the common approach would be to take a local maximum of this function like this. We have taken the local maximum of both the functions. So the region size for which the maximum is achieved should be covariant with the image scale. So if the image scale is S1 here and the image scale is S2 here, so the maximum which we have found, or the maximum point which we have found for the region, should be covariant with these image scales. Note that this scale invariant region size is found in each image independently. So you would find many responses, many such responses for different scales. So a good function for scale detection has one stable sharp peak. As we already discussed in our previous lecture in the corners, that we need to find the distinctive patterns. And how can we do that? We have already studied this kind of patterns where we want to find a good single response. If we can find a good single response, we can easily discriminate, or we can easily match the patch which we want to find in another image. But if we cannot find a single response, then it will be very difficult for us to match that one. So in this, and by finding a good single response, we meant that it should have the gradient in all directions rather than a single direction. So in this case it's a flat region, and we do not want to detect such region here. In this case there are some peaks, but there are many responses, so we do not want multiple responses, we need a single response. This is one of the example to find a single response, which would help us to compare and to match a particular patch in another image with reference to the image which we have used for finding the patch. So for usual images, a good function would be one which responds to contrast, sharp local intensity change, which is one of the way to get a single response. So the functions for determining scale is, we have already discussed this in our age detection class, that how we can use this function. We can design a kernel. A kernel is a kind of a window, and it is convolved with the image which we have provided. So it will apply the convolution from left to right and top to bottom. and then it will yield such responses. So for kernels, we have already discussed about the Laplacian kernel, and Laplacian kernel is susceptible to the scale size, which is the sigma. So one way is to apply the Laplacian kernel, and another way is to apply the difference of Gaussians. We will discuss about the difference of Gaussians in detail, but till now, let's consider this, that the difference of Gaussians and Laplacian kernel can be used for such purposes, where Gaussian function is given by this formula. So you should also know that both of these kernels are invariant to scale and rotation, and I'll explain you why these both kernels are invariant to scale and rotation. So basically, the Gaussian function here in Laplacian is applied in x direction and y direction with respect to multiple scales here, which is represented by this sigma value. And the difference of Gaussians, what it uses is it takes on multiple scales, and it performs a kind of a difference between the previous version of the scale and the new version of the scale. So we can get a good approximation of the Laplacian with respect to the difference of Gaussian, but remember the difference of Gaussian is quite faster than the Laplacian kernel. And you can see here from the responses that the difference of Gaussian is approximately yielding the same response as the Laplacian of Gaussian. So if we want a particular approximation of Laplacian, but we have the time constant or the computational time constant, then we can use the difference of Gaussian right away. So the Harris Laplacian, what it does is it finds the local maximum of the Harris corner detector in space. So this is a kind of a scale space. As you move up, you are increasing the scale, and you compute the corners in x and y direction. So you can see that it detects this corner, and it matches the same corner, looks for the same corner in multiple increasing scales, and once it finds, it will return that particular scale, the Laplacian in that particular scale. So this is a kind of a response which we get if we get a particular corner in a particular scale. So this is a kind of a characteristic scale plot where we get a single response, a single peak response. But we can also use SIFT. We will discuss about SIFT in detail in the next video series. So SIFT is a kind of a scale invariant feature transform, and it has been proposed by Loy in 2004. What it does is it finds the local maximum of difference of Gaussians in space and scale. So it means that what it does is it performs difference of Gaussians in x direction and y direction with respect to the varying scales. So see this, this is a kind of a scale like a filter convolved with the image, and this is again increasing scaled functions convolving with the image. And once you will have these responses, what it does is it will get the first scale and the second scale and performs the difference between this pair, and then computes the difference between this pair, and then computes the difference between this pair, and then computes the difference between this pair. So basically we get these responses, these difference of Gaussians, and you will see that if you just have this particular image, the original image, and if you blur it with the Gaussian function and compute the difference, you will get this response. Similarly, if you compute the difference between this blurred version and more blurred version with respect to the scale, increasing scale, then you will get this response. We have already discussed in the age detection lecture that if you increase the scale, sorry, not age but filters lecture, that if you increase the scale you will get more and more blurred image. So if you increase uh, the size of the kernel, of course you will again get more and more blurred image. So basically increasing the sigma value or increasing the kernel size will yield the same response, that is it will blur the image. So as you are blurring the image, you will see that you are getting more and more different responses from difference of Gaussian. So what we can do is we can choose the extrema within our 3 by 3 by 3 by 3 by 3 by 3 neighborhood. So in this case, this x is selected if it is larger than all other 26 neighbors, or if it is smaller than all other 26 neighbors. So it's like computing an extrema or a minima. So the 26 neighbors is like 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 24 25 26. So all these 26 neighbors either should be larger or smaller than this x value. Then and only then we can consider this x value as an extrema. The example of the Gaussian kernel is shown here. So if we have a kind of a original video means that we have considered the first frame of it, and then we blur the subsequent frames. So what we do is, if we blur the subsequent frames with a Gaussian kernel, what happens is we get this kind of response. So if we compute the difference of Gaussian from k1 and k2, we get this. If we compute the difference of Gaussian from k1 to k3, which is a subsequent frame from this k2, then we get this response. And as you move forward, you get these kind of responses. So basically you can actually go to this link and you can find a particular demo for this kind of stuff, which is difference of Gaussian. So at different resolutions of kernel size, we see different fine details of the image. In other words, we can capture key points at varying scales, and that's exactly what we want. We want to find a particular key point at different scales, and then this is actually our first step. So if you just recall what we discussed in here, we find a distinctive key points, and then we define a region around key point. We extract and normalize the region content, and we compute a local descriptor from the normalized region. So what we are trying to do is, once we find a set of distinctive key points, we want to find the regions at varying scales. So if we can find the regions at varying scales, then we can easily define the region and then can extract the local descriptors for further purposes like image matching or image stitching and so forth. So what we have discussed so far is that given two images of the same scene with a large scale difference between them, we want to find the same interest points independently in each image, so that the interest points would be the same and invariant to the scale or invariant to the scaling operation. The solution is to search for maxima for suitable function in scale and in space. So it's like varying the scales and computing the maxima and selecting that particular response. So one of the method is the Harris Laplacian, which was proposed by Schmidt and the team. The title was Maximize Laplacian over Scale, Harris measure of corner response over the image. And then we have the SIFT, which is most commonly used one, and SIFT was very popular from 2005 to 2012, before the advent of deep learning strategies which yielded better results. But before that, SIFT was used extensively for object recognition, object detection, and other recognition stuff. And what it does is it maximizes the difference of Gaussians over a scale n space. The advantages of invariant local features are locality, so we get the location, the exact location. So the features, if the features are local, they are immune, or you can say uh, they are not affected by the occlusion or the clutter. Of course, the performance gets degraded, but it does not get degraded to an extent where you cannot use it. So it's robust in terms of occlusion and clutter. The occlusion is a kind of that, um, like if we have, let's say, if let me draw. So if we have a certain image and we kind of, uh, as the video goes forward, this kind of object crosses it and blocks it blocks the view of this part. So this is a kind of a partial occlusion where we can only see this part of the image, and this part of the image is a kind of hidden with respect to a particular object. So uh, the the location allows us, the locality, the local features allows us to be prone to this kind of occlusion and clutter. And also distinctiveness, we have already discussed this feature in our previous class and in this class, that we need to find the distinctive patterns which can be easily discriminated or easily what you say is classified. So if the individual features can be matched to a large database of objects with respect to its distinctiveness means they are unique or they are different from the normal features. So it will be like if I am detecting a face, so face have some unique features like eyes, nose, and lips, and all other stuff. So these are the distinctive features which discriminate between the face and a box. So if we keep a box in front of the face, like two images, one is of the box and one is of the face, and if we are not extracting distinctive features, then it will yield the same result for both of these images, that they both are same, because the box are a kind of the same skin color and all that stuff. But if you detect the distinctive key features, then you would know that there are some features which are missing in the box. So these both images belong to different categories rather than a single category. Quantity, so we will discuss this when I'll show you a demo. So it will be a problem uh, if you detect so many features. So if there are many responses, it will be very difficult to compare them. So it will be easier if you can extract a certain amount of features. So it will be easier to compare them and it will be easier to match them. Otherwise it will take a lot of computational complexity to compare all of those features, and sometimes if there are many features, there is a chance of false detection. So if you are comparing to many features and some of the features gets matched, which are again false points in the first place, then you may classify uh, the the object in the image as of a different category. So that's a kind of a false positive. So it should not be detecting the a certain category which is not present in that particular image, and that's because there are many feature points or many feature responses which we need to compare anyway in between two images. Efficiency is close to real-time performance, and this means that if we are applying it to a real life environment, it should be faster, and it will be faster if there are less feature points to compare, and if the features are distinctive, and if the features are particular, like it has a good localization. So these above 3 points contribute to this fourth point, which is the efficiency. And there is extensibility, so it should be easily extendable to wide range of different feature types with each adding robustness. So it means that if it should work with other techniques as well, it should work with other feature types as well, it should not be restricted to a single feature type. So you can also consider this as a flexibility trait. So we'll discuss this shift in detail in the next video series, in the next video lecture which I am going to upload. So till then, if you have any questions regarding this lecture, please let me know. If you have any query with respect to this lecture, or if you cannot understand anything, let me know, and we will discuss it in our live session class. So don't worry about that. If you are not I am again repeating, if you are not understanding the mode of my language, don't worry, we will discuss each and everything in our live session. If you do not understand a particular concept, we will discuss that as well in our native language, so it will be easier for me to understand, to make you understand some of the points rather than the whole lecture uh, in that 1 hour. But remember that while taking the live sessions, there are many problems. That's why I am pre-recording this video, so you can listen them at your convenient time, and then the live session will be there to explain each and everything in easy words or in native language which you are able to easily grasp. So till the next video comes up, goodbye for now.